All right, we just talked about intervals where a graph might be concave upward or concave downward, and that points of inflection are the points on the graph where the concavity changes between concave upward and concave downward. But we haven't talked about how to tell if a function is going to be concave upward or concave downward somewhere. And there's a very easy way to tell this, a very simple concavity test based off of the second derivative. If the second derivative of a function is positive for all x in an interval I, then the graph of f is concave upward on that interval, which means it kind of looks something like a smile. Whether it's the decreasing part or increasing part, we don't know, but it is concave upward if the second derivative is positive, and if the second derivative is negative on an interval, then it is concave downward. I like to think of a positive second derivative as a smile. We smile at positive things. And a negative second derivative as a frown, because we frown when we see negative things. So that's the easy way to remember which ones. So that is how we can tell whether it's going to be concave upward or concave downward. But in a sense, even more importantly, we want to know how these second derivatives are going to give us information about extreme values, because we really want different ways of figuring out if we're going to have a local maximum or a local minimum, or neither at a critical number, because we want to be able to use that information to sketch the graph. And we have a test that's going to help us called the second derivative test. The second derivative test says, suppose that the second derivative is continuous near C and f prime of C equals 0. So we know we're at a critical number because the first derivative is equal to 0. If the second derivative is greater than 0, then f has a local minimum at C. And if the second derivative is less than 0, then f has a local maximum at C. So this is one way to help us identify if we have a local minimum or a local maximum at a critical number. Note that this does not tell us anything about critical numbers where the first derivative doesn't exist, because if the first derivative doesn't exist, then the second derivative is not going to exist. So this test fails there. It also doesn't tell us anything if the second derivative is equal to 0 at that point. We need either the second derivative to be positive or the second derivative to be negative for this test to tell us anything. So let's dig into an example so we can see exactly how this is going to help us. Find the critical numbers of f of x equals 2x cubed plus 3x squared minus 12x, and use the second derivative test to determine which give local maximum and minimum values. Now, I have already covered this problem in a previous section looking at the first derivative test, where we had to make a sign chart and fill all of that out to figure out when it was increasing and decreasing, to figure out if there were local minimum or maximum values. Let's see how this process is different with the second derivative test. Now, we first need to find the critical numbers, which means we need to take the first derivative. And when we do that, we get 6x squared plus 6x minus 12. Now, the critical numbers will happen when this is undefined or equal to 0. And it's not undefined anywhere, so we just need to see when this equals 0. We can factor out a 6, giving us x squared plus x minus 2. And then we can factor that even further, giving us x plus 3 times x minus 2. So our critical numbers are going to be at negative 3 and positive 2. And before, like I said, we would have to make a sign chart for the first derivative test, but we're using the second derivative test. So let's differentiate the first derivative to get our second derivative. So the derivative of 6x squared is 12x plus the derivative of 6x is 6, and the derivative of a constant term is 0. Now, all we have to do is we have to see if this is positive or negative at our critical numbers, and that's going to tell us if we have a local minimum or a local maximum. We do want to make sure that this follows all of the requirements of the second derivative test. This second derivative is continuous everywhere because it's a linear function. And we saw that the first derivative was 0 for these critical numbers, so everything fits. So we just need to evaluate this at our critical numbers and see what's up. So we can start by evaluating this at -3. 12 times -3 is -36 plus 6. That's going to be -30. Since the second derivative is negative, we know that this is going to be a local maximum. And that's, remember, because a negative second derivative meant a frown, concave downward, so that is a local maximum. So we have a local max at c equals -3, or x equals -3. And then if we do the same thing, but we evaluate this at 2, 12 times 2 is 24, and 24 plus 6 is +30. Positive means a smile. That means we have a local minimum there, a local minimum at c equals 2. If we want to figure out the function values at that point, we'd have to plug in 2 and -3 into our original function, but we weren't asked for that. We just wanted to know if these corresponded to local maximum or local minimum values, and that is exactly what we have. Now, I want to talk about pros and cons of the second derivative test compared to the first derivative test. Now, one advantage of the second derivative test is it's a lot less work. This is a lot less work than doing that table of values. We just took the derivative to get the second derivative and plugged in numbers, and it was pretty easy. Not that much work there. So on one hand, this might be less work than the first derivative test. But the downside is that it doesn't always work. If the second derivative was 0 for either of these, it would not give us any information. And similarly, if the second derivative was undefined, or even if the first derivative was undefined, again, that would give us no information. And so in those situations, we would have to go back and do the first derivative test to get an idea of if we have a local maximum, a local minimum, or neither. So I like this test because it's less work, but it doesn't always give us a result. So it's unfortunately not something we can always rely on. We need to make sure we understand both of the derivative tests.